Welcome back to Mr. Vaughn's classroom. Before we get started, I'd like to ask you to please hit the subscribe button, give this video a thumbs up, and please engage in the comment section below. Today, we're looking at Unit 5, Introduction to Exponential Functions. Lesson 19, Which One Changes Faster? And in my class, this is the last lesson we'll look at before the end of Unit 5 test. The learning goal today is to compare linear and exponential functions as they continue to increase. We have one learning target. We'll come back and take a look at this at the end of the lesson, but as we go through the practice problems, please keep this learning target in mind, and if at the end of the lesson you still have any questions about it, please drop a comment below, and I'll get back to you with any help I can offer. So the learning target for today says that you can use tables, calculations, and graphs to compare growth rates of linear and exponential functions and predict how the quantities change eventually. Our first practice problem says functions a, b, c, d, e, and f are given below. Classify each function as linear, exponential, or neither. Now, to demonstrate this, I'm going to start off by showing you how to do this in table format. So for number 1, we have x, and we have a of x. And so if we started with 0, 0 times 3 is 0. Then if we used 1, 1 times 3 is 3. If we used 2, 2 times 3 is 6. If we used 3, 3 times 3 is 9. And if we used 4, 4 times 3 is 12. Notice each time we are adding 3. That means this is linear. Now, let's look at number 2. We have x as our input, and we have b of x as the output. When x is 0, 3 to the power of 0 is 1, because anything to the power of 0 is 1. If x is 1, then 3 to the power of 1 is 3, because anything to the power of 1 is itself. If x is 2, then 3 squared is 9. If x were 3, then 3 cubed is 27. And if x was 4, then 3 to the power of 4 is 81. What's happening is that we're taking the value of the output and we're multiplying it by 3 over and over again. That means this is exponential. Number 3. We have x for the input. We have c of x for the output. If x were 0, then 0 cubed is 0. If x were 1, then 1 cubed would be 1. If x were 2, then 2 cubed, 2 times 2 is 4, times 2 is 8. If x were 3, then 3 cubed, 3 times 3 is 9, times 3 is 27. And if x were 4, 4 times 4 is 16, times 4 is 64. You can see we are not adding by the same amount every time, and we are not multiplying by the same amount every time. So this is neither. Number 4, we have x as the input, and we have d of x as the output. If x was 0, then 0 times 3 is 0, plus 9 is 9. If x is 1, 1 times 3 is 3, plus 9 is 12. If x is 2, 2 times 3 is 6, plus 9 is 15. If x were 3, 3 times 3 is 9, plus 9 is 18. And if x were 4, then 4 times 3 is 12, plus 9 is 21. We can see that we are adding 3 each time. That makes this linear. Number 5. We have x as the input, and we have e of x as the output. So when x is 0, 3 to the power of 0 is 1, times 9 is 9. If x is 1, then 3 to the power of 1 is 3, times 9 is 27. If x is 2, then 3 squared is 9, and 9 times 9 is 81. If x is 3, then 3 cubed is 27, and 27 times 9 is 243. And if x is 4, then 3 to the power of 4 is 81, and 81 times 9 is 729. To go from 9 to 27, we multiplied by 3. Then we multiplied by 3 to get 81. Then we multiplied by 3 to get 243. And we multiplied by 3 to get 729. We're multiplying by 3. That means this is exponential. And lastly, number 6. we have x as the input. We have f of x as the output. When x is 0, 3 times 0 is 0, times 9 is 0. When x is 1, 1 times 3 is 3, times 9 is 27. When x is 2, 2 times 3 is 6, times 9 is 54. When x is 3, 3 times 3 is 9, times 9 is 81. And when x is 4, 4 times 3 is 12, times 9 is 108. If you notice, we're adding 27 each time. That means it is linear. So these are your answers. Number 1, number 4, and number 6 are all linear. Notice what they have in common. X is a base number being multiplied by 3. Number 4, x is a base number being multiplied by 3. And on number 6, x is a base number being multiplied by 3. This results in a linear function each time. Next, we said that number 2 was exponential, and we said that number 5 was exponential. Notice that in number 2, x is the exponent. And in number 5, x is also the exponent. That makes it an exponential function. And then the only one that was neither was number 3, and this one had x as a base number being taken to a power. So if you're adding the same amount every time, it's linear. If your equation has x as a base number being multiplied by a number, then it's going to give you that linear equation. If you're multiplying by the same number every time, then that is exponential, and that ends up looking like x being the exponent and then having a base number. That results in your exponential function. If you have any other questions about this practice problem, please leave a comment below, and I'll get back to you with any help I can offer. Our next practice problem says here are 4 equations defining 4 different functions, a, b, c, and d. List them in order of increasing rate of change. That is, start with the one that grows the slowest and end with the one that grows the quickest. So what I want you to notice is that in every single one of these, x is a base number. Also notice every single one of these is written in the linear slope-intercept format. Y equals mx plus b. This is linear slope-intercept. So, if this is linear and this is slope-intercept format, then the m, the number that is with the x, is our slope. That is our rate of change. So the slowest is going to be the smallest m. So that's going to be c of x. Next would be b, because it has a slope of 3. So b of x. Next would be d, because it's got a slope of 4. And then lastly, a would grow the fastest because it has a slope of 5. So we'll say that m equals 1 on c, m equals 3 on b, m equals 4 on d, and m equals 5 on a. If you have any questions about how to answer this practice problem, please leave a comment below and I'll get back to you with any help I can offer. Our next practice problem says technology required. Function f is defined by f of x equals 3x plus 5, and function g is defined by g of x equals 1.1 to the power of x. Number 1, complete the table with values of f of x and g of x. When necessary, round to 2 decimal places. So first we'll look at f of x. We're going to take each number and we're going to substitute it in for x. So when x is 1, f of x would be 3 times 1 is 3, plus 5 is 8. When x is 5, then f of 5 would be 3 times 5, which is 15, plus 5 is 20. Next, we have x is 10, so f of 10 would be 3 times 10, which is 30, plus 5 is 35. And lastly, we have x is 20, so f of 20 equals 3 times 20, which is 60, plus 5, which is 65. Next, we're going to look at g of x. When x is 1, then g of x is 1.1 to the power of 1. Anything to the power of 1 is itself. So this is 1.1. Next, we have x is 5. So 1.1 to the power of 5. We can put that in a calculator. 1.1, we use the x to the power of y button, and we tell it the exponent is 5. And if we round to 2 decimal places, that is 1.61. Next, we have x equals 10. So g of 10 would be 1.1 to the power of 10. So 1.1, again, we use that x to the power of y button, and we tell it the exponent is 10. Rounded to 2 decimal places, this gives us 2.59. And the last entry on the table is when x is 20. So g of 20 would be 1.1 to the power of 20. On a calculator, we would type 1.1, then the button that says x to the power of y, and we tell it the exponent is 20. And rounded to 2 decimal places, this would be 6.73. Now, number 2 wants to know which function do you think grows faster? Explain your reasoning. Well, if we look at f of x, it's grown from 8 to 65. That's an increase of 57. G of x has only grown from 1.1 to 6.73, an increase of 5.63. If we're thinking about multiples, from 8 to 65 is an increase of just over 8 times, and 1.1 to 6.73 is an increase of just over 6 times. So at this point, f of x is increasing faster than g of x. Now, number 3 wants us to use technology. So for us, that will be the Desmos.com calculator. And they want us to create graphs representing f and g. And then they ask us, what graphing window do you have to use to see the value of x where x becomes greater than f, or where g becomes greater than f for that value of x? So we go to the Desmos.com calculator, and in the first one, we had 3 times x plus 5. So now we can see this red line represents that graph. The next one was 1.1 to the power of x. This blue line is the one representing g. And they want to know, where would we need to get to for the blue line to overtake the red line? So we can zoom out and drag it around, and what we will eventually see is this point right here. So we'll zoom in so we can get a better idea of where this is. And at x equals 53, the red is still higher. But by the time we get to x equals 54, now g is higher. So to answer the question, x needs to reach 54 before g is greater than f. If you have any questions about how to answer this practice problem, please leave a comment below and I'll get back with any assistance I can offer. Our next practice problem says functions m and n are given by m of x equals 1.05 to the power of x, and n of x equals 5 over 8 times x. As x increases from 0, number 1 which function reaches 30 first, and number 2, which function reaches 100 first. So what we're going to do is we're going to go into the Desmos.com calculator, and we're going to put these two functions in, and then we'll be able to see which one reaches a y value of 30 first, and which one reaches a y value of 100 first. So in the Desmos.com calculator, we can click in this first entry, and we had 1.05 to the power of x. So this red line right here represents that equation. Then we click the entry below it, and the other equation was n of x equals 5 over 8 times x. And this blue line represents that one. So what we're looking for is to see which one reaches a y value of 30 first. So we're just going to keep dragging these, zoom out a little bit, and we can see right here, when y equals 30, the first line to hit it is the blue line. The blue line represents the linear equation, so that is n of x. So n of x reaches 30 first. Now, number 2 wants to know which function reaches 100 first. So we're going to go back to the Desmos calculator, and we're going to keep moving this until we get up to 100. And if we zoom out a little bit, we can see where they both hit 100, but the red line clearly does it first. It does it right around 94, and the blue line doesn't do it until around 160. And the red line represents 1.05 to the power of x, which is the exponential equation. And that is m of x. So for number 2, m of x reaches 100 first. And I'm just going to put in parentheses here that this one was exponential, and on the other one, I'll put in parentheses that it was the linear function. So even though the linear function reached 30 first, eventually the exponential function grew quicker and overtook it. If you have any questions about how to answer this practice problem, please leave a comment below, and I'll get back to you with any help I can offer. Our last practice problem, the functions f and g are defined by f of x equals 8x plus 33, and g of x equals 2 times 1.2 to the power of x. Number 1, which function eventually grows faster, f or g? Explain how you know. So what you need to realize is that f of x is in the slope-intercept form for a linear equation. G of x is in the format for an exponential equation. y equals a times b to the power of x. So, when we're trying to determine which one eventually grows faster, exponential functions eventually grow faster than linear. So g of x eventually grows faster than f of x. Number 2. Explain why the graphs of f and g meet for a positive value of x. So this is based on you being able to identify the starting values, which are the y-intercepts. In a linear equation, that's this number without the x, 33. In an exponential function, that's this number that does not have an exponent, 2. So what we know is f of x starts higher because 33 is greater than 2, but g of x eventually grows faster and crosses above f of x. If you have any questions about how to solve this practice problem or any other practice problem we've gone over in this lesson, please leave a comment below. Before we end this lesson, I want to go back, take a look at the learning target, and double check that you've learned everything you should have so that you're prepared moving forward. Before we finish up, let's review this learning target. It says that you can use tables, calculations, and graphs to compare growth rates of linear and exponential functions and predict how the quantities change eventually. So this simply means you understand how to look at tables and determine which functions are linear and which functions are exponential. You know how to look at their equations and determine which one is linear and which one is exponential. And you know how to look at graphs and tell from their shape which one is linear and which one is exponential. Then you understand that exponential functions always eventually change quicker and overtake the linear functions. If that all makes sense to you, you're right where you should be, and you're in good shape moving forward. If you still have any questions about this, please leave a comment below, and I'll get back to you with any help that I can offer. If you found this video useful, I ask that you please hit the subscribe button, give this video a thumbs up, and leave a comment below. And if you did find this video helpful, I'm going to put a link to another video you can check out, and keep improving your math skills. I look forward to seeing you in the next lesson.